An observation of dilatant fluids. Newtonian fluids are fluids that display a linear relationship between shear stress and rate of strain, given a constant temperature and pressure. That is, that as shear stress in a fluid increases, the rate of strain increases a proportional amount. Water is a prime example of a Newtonian fluid. For example, as you increase the pressure in a water bottle, the water's rate of strain, the velocity out of the bottle in this case, will increase a proportional amount. Interestingly enough, for Newtonian fluids, the proportionality constant between shear stress and rate of strain, also the slope of the stress versus rate of strain graph, is the viscosity of the fluid. Viscosity is a measure of the resistance of a fluid which is being deformed by stress. Viscosity describes a fluid's internal resistance to flow and may be thought of as a measure of fluid friction. In everyday terms, it is described as thickness. Water is a very low viscosity and thus has little resistance to stress and flows freely. Honey, another fluid exhibiting Newtonian flow, has a much higher viscosity and therefore higher resistance to stress. This can be observed since honey flows at a lower velocity than water given the same shear stress. This short graphic shows the difference between fluids with different viscosities. The top fluid has a very low viscosity and so when acted upon by a force, such as the falling cube, flows freely without much resistance. The bottom fluid, on the other hand, has a high viscosity and resists flow much more than the top fluid when acted upon by the force. Dilatant fluids, also known as shear thickening, are a special class of non-Newtonian fluids and the focus of this video. Dilatant fluids experience a nonlinear relationship between shear stress and rate of strain, and as a result can exhibit some unusual properties. Essentially, their apparent viscosity changes depending on the applied stress. Materials exhibiting this relationship flow like a viscous fluid under low stress, but their apparent viscosity increases dramatically under high stress. The apparent viscosity of some dilatant fluids increases so much under stress that they actually behave like solids. Silly putty is an excellent example of a non-Newtonian fluid displaying dilatant flow. Here we have sped up the video of a pool of ordinary silly putty atop a small hole, approximately half an inch in diameter, to 10 times the real time. Silly putty's viscosity is quite high, even under no external forces, and has a high resistance to flow. However, as you can see, silly putty flows similarly to a highly viscous fluid over long periods of time. In a different circumstance, when the silly putty is subjected to high stress, it bounces much like a bouncy ball or elastic solid. After it bounces and is at rest with no other forces acting upon it other than gravity, we can observe it to ooze once again like a viscous fluid. Another material that exhibits non-Newtonian flow is the suspension of cornstarch in water. Under low stress, it behaves like a highly viscous fluid. Under high stress, the cornstarch molecules are closely compacted into a crystalline structure, which greatly increases friction and gives rise to its solid properties. Here you can see a rubber ball bouncing on top of a liquid. The ball bounces like it would on a solid since the cornstarch suspension compacts into a crystalline structure under the stress. Similarly, when a person punches the liquid with force, the suspension strains very little and acts like a plastic solid. When a person runs their hand strongly against the suspension, you can see how it parts and crumbles like a plastic solid would. However, as soon as the stress is removed, the suspension flows like a liquid to fill in the spaces created by the stress. An interesting example of non-Newtonian behavior can be demonstrated by placing a suspension of cornstarch in water, the same suspension shown in previous examples, atop a speaker emitting low-frequency sound waves. Here we can see water and the cornstarch suspension side by side. Both speakers emit 20 Hz sound waves at the same intensity, and the intensity of the sound is slowly increased. The water, a liquid with low viscosity, proportionally strains to the intensity of the sound, bouncing higher and higher. The cornstarch suspension, which has a much higher viscosity even at rest, strains but much less. Once the intensity reaches approximately 60 decibels, the cornstarch suspension begins to display unusual characteristics. Here we can observe this phenomenon more closely. This unusual movement is due to the constantly changing apparent viscosity of the fluid. As the speaker emits each sound wave that propagates to the suspension and applies stress on it, the suspension quickly behaves like a solid and then back like a liquid until the speaker emits the next sound wave. This happens 20 times a second and causes the odd-looking movement you see now. Whenever the speakers are stopped, the suspension no longer has any external forces acting upon it, besides gravity, and resumes characteristics of a viscous fluid, flowing back into an ordinary puddle. Here we can see the same effect on a different suspension of cornstarch in water that has a higher viscosity at rest. Just as the other suspension, once all external forces cease, it flows again like a liquid. Having looked at only a couple of examples, we can see that dilatant fluids are an extraordinary class of non-Newtonian fluids that display interesting and sometimes counterintuitive properties. Understanding them a little bit more is not only interesting, but has wide applications in the engineering world. Next time you play with some silly putty, maybe you will have a greater appreciation of its unique properties and the science behind it.